Hello everyone. So it's good to see you all again in the part 3 of P block elements 2. Yeah, I know it's been quite a while since we are rushing up portions in the offline classes, so we couldn't come very often through online and post our video in the YouTube. So there is a little bit of lag. It happens quite a while, right? So in this class, what are we going to deal with? The part 3 contains something which has a great aspect to deal with an element called phosphorus. In the last class we have done with ammonia, we have seen what is nitrogen, its occurrence, physical properties, chemical properties, etc. And in this class we are going to look into the phosphorus, right? Phosphorus, it exists in different allotropes. How? And what are those allotropes? See, the allotropes of phosphorus includes the white phosphorus or yellow phosphorus. How do we obtain this white phosphorus or yellow phosphorus? You have to take this phosphate rock, and to that you have to add silica and coke, which is nothing but the powdered charcoal, for which you have to generate the temperature of about 1770 Kelvin, not with the flame but with the electric discharge, which means through an electric furnace. If you do it, you will be getting white or yellow phosphorus. Both are quite similar. The properties are very quite common. That's why it is named after white or yellow phosphorus. So preparation is quite simple. Phosphate rock, you have to heat the phosphate rock with silica and coke. For that you need not use the flame. In order to raise the temperature to about 1770 Kelvin, you have to use the electric discharge, which is electric furnace, so that you will be getting white or yellow phosphorus. Now its properties. See, if you are preparing this white phosphorus very freshly, I mean if you prepare just right now, you can see the phosphorus in the color of white, which is nothing but colorless. You will not be able to find any color. How does it turn yellow? Because in the white phosphorus, due to oxidation, what happens? There will be a formation of a red layer of phosphorus in the middle. It means in the white phosphorus, in the middle of the white phosphorus, you will be able to find the formation of a red phosphorus. So because of that, if you look it through your eye, it looks like yellow in color. That's why it is named after yellow phosphorus. Actually, white phosphorus, in a layer, you will be able to obtain the red phosphorus. Because of the formation of the red phosphorus in the white phosphorus, it appears yellow. That's it. And this phosphorus is poisonous in nature, and you will be able to find it in garlic smell. You know the smell of a garlic, need not to go further again. And this phosphorus has an ability to show a property called phosphorescence, which is nothing but it has a capability to glow in dark because of the process called oxidation, which means this phosphorus is capable of oxidizing itself and capable of exhibiting color. That's what here it called phosphorescence, which shows glows in dark. And it can ignite at very low temperature just like that. In the presence of a very small amount of an oxygen, it forms phosphorus pentoxide so easily, even at the room temperature itself. See, this phosphorus, which is P4, if it reacts with the oxygen, atmospheric oxygen, it easily forms phosphorus pentoxide, P2O5, so easily. So this happens quite here in the room temperature itself. So these are all the basic properties of this white or yellow phosphorus. Coming again, so freshly prepared phosphorus will be colorless. It appears yellow because of the formation of a red layer of a phosphorus in the white phosphorus, and it is quite poisonous and capable of exhibiting garlic smell. It shows a peculiar property called phosphorescence, which means it is capable of glowing in dark, and it can ignite at very low temperature itself. And this phosphorus is capable of reacting with the molecular oxygen and forms phosphorus pentoxide even in the room temperature itself. Next one. The next allotrope is red phosphorus. How do we get the red phosphorus? Very easy. When the white phosphorus is heated at 420 degrees Celsius, in the absence of air or light, you will be getting red phosphorus. White phosphorus turns red phosphorus at 420 degrees Celsius in the absence of air or light. As we have seen in the white or yellow phosphorus, it is poisonous. This red phosphorus is not poisonous. There it shows phosphorescence, here it does not show phosphorescence. There it is capable of igniting at low temperature itself, their room temperature itself it is capable of igniting. Here it is not capable of igniting at the room temperature itself. There it glows in dark, here it does not glows in dark. The properties of this red phosphorus and the white phosphorus are quite opposite to each other. You can look at it directly. And this red, if I have a red phosphorus, in order to turn into a white phosphorus, what I must do? I need to boil this red phosphorus and I have to condense it with the help of a water. Last we have seen in distillation. See, I have to boil this red phosphorus, it turns into a vapor. Once the vapor gets condensed, it will just become as the freshly prepared white phosphorus, and the whole thing should be carried out in an inert atmosphere. If not, oxidation will occur. So that's what. Right. Then next one. Black phosphorus. How do you prepare black phosphorus? When the white phosphorus, if you have a white phosphorus, if you heat it at 475 Kelvin in an inert atmosphere by maintaining at high pressure, you will be having this, you will be getting this black phosphorus. White phosphorus turns black phosphorus at 475 Kelvin in an inert atmosphere at a high pressure. That's all. And this property of this black phosphorus is doesn't conduct electricity. Among all the phosphorus, most stable form. If it is more stable, it will not react so easily. That's why it is less reactive. Then, general properties. This phosphorus actually exists as P4. How does it exist as P4? And this P4 has a layered structure, one beneath the other. So, layered structure. And this phosphorus is capable of conducting electricity when there is an addition of an impurities like the other elements, trivalent and the pentavalent impurity. If you add it, you will be able to make this phosphorus to conduct electricity. So, definitely if something is capable of conducting electricity on the addition of an impurities, it must be a semiconductor. So, that is why it acts as a semiconductor. As I have said, phosphorus exists as a P4. If you look at the chain that has been formed by it, it looks polymeric, which means it repeatedly form the P4 units. That those phosphorus units are linked tetrahedrally. Tetrahedral in the structure, you know it, three phosphorus will lie in the below the plane and one phosphorus will lie above the plane. So, with an angle of 109.5 degree, that usually happens here. Then nitrogen belongs to the same group where the phosphorus belongs, but nitrogen is more stable in this form, N triple bond N, which is more stable and it attains octet. Phosphorus here, it is more stable in P single bond P. So, quite opposite to each other here. And apart from this, red phosphorus we have seen, black phosphorus we have seen, white or yellow phosphorus we have seen. We have also come across the scarlet and violet phosphorus, but still it is not given in our syllabus. So, we will restrict with this itself. So, the general property says it is a layer structure, semiconductor, polymer, tetrahedral unit, P single bond P is more stable than compared to the P triple bond P. Scarlet and violet phosphorus is also available. The next one, reaction with an air. It is very easy. It forms phosphorus trioxide, it forms phosphorus pentoxide so easily. Very spontaneously it reacts. So, when phosphorus reacts with oxygen, it forms phosphorus trioxide, and the same phosphorus, if it reacts with an oxygen, it forms phosphorus pentoxide, P2O5 or P4O10, you can write anything. Right, to balance with, I will make it as 2 here, so oxygen becomes 6. So, to balance with, I will make it as 2 here, so oxygen becomes 10, so I will make it as 5O2. So, this is the reaction for this particular reaction with an oxygen. Then, reaction with chlorine. See, red phosphorus will react with chlorine once you heat it, but this phosphorus will react with chlorine so easily, but yellow phosphorus, if you look at there, this react very violently at room temperature to form phosphorus pentachloride and phosphorus trichloride. If you have a red phosphorus, just on heating it will react with the chlorine, but yellow phosphorus will react with the phosphorus to form phosphorus pentachloride or phosphorus trichloride when you heat at room temperature, but the reaction takes place so violently. Reaction is quite common. So, P4 reacts with Cl2 to form PCl3, this is phosphorus trichloride. So, chlorine becomes 12, so I will make it as 6. Then phosphorus reacts with chlorine to form phosphorus pentachloride PCl5. So if I make it as 4 here, so chlorine becomes 20, so I will make it as 10 here. So that's it with this. The third reaction is the reaction of phosphorus with an alkali. It clearly shows that phosphorus can also act as a reducing agent over here. Come, see the phosphorus over here P4 will react with sodium hydroxide solution NaOH along with the water molecule, and the whole reaction is taking place at inert atmosphere to form phosphine, which means phosphine is a poisonous gas which actually goes out, harmful gas, and we have got sodium hypophosphate Na2 H2PO2 or NaH2PO2 sometimes. Okay, this is the whole thing that happens over here. Then next one, reaction with nitric acid. So reaction with the nitric acid here is the whole reaction is catalyzed by iodine crystal, which also clearly shows that here phosphorus is an reducing agent. We will look at it. The phosphorus P4 will react with nitric acid HNO3 to form orthophosphoric acid H3PO4, then nitrogen dioxide NO2 plus H2O. So to balance with, I will make it as 20 here, I will make it as 20 here, I will make it as 4 here. So hydrogen totally it is 20 here, here it is 12. So to balance with, I will make it as 4. So the total thing is completely balanced. Yes. So that's it with this. So here the oxidation phosphorus is 0. Here if you look into it, the oxidation of phosphorus over is plus 5. So it is clearly shows that when phosphorus gets oxidized, it must be a reducing agent. So that's it. Then reaction with a metal. With calcium and magnesium, it clearly forms a phosphide so easily. See, when calcium reacts with phosphorus to form calcium phosphide Ca3P2. So to balance with, I will make it as 6 here. Similarly magnesium. Magnesium is also belongs to the group 2. So stoichiometry will obviously be the same. 2 molecules of Mg3P2. Then with sodium and the potassium, the reaction takes place vigorously and forms when sodium reacts with potassium, phosphorus, it forms Na3P, sodium phosphide. If I make it as 4 here, so sodium becomes 12, so I will make it as 12 here. So that's it with this. The next one, uses. Red phosphorus is widely used in the manufacturing of this matchboxes, and also widely used in the manufacturing of various alloys like phosphor bronze is an alloy which has a combination of copper and phosphorus of a percentage of between 0.01 to 0.35% over here. See, what is the reason for the addition of phosphorus in such alloy? Because it is quite water resistance. It has a property of water resistance and the strength of an alloy is being increased, which means stiffness is enhanced. That's why. That's the reason here the phosphorus is being added for the manufacturing of an alloy. The name of an alloy which is given as an example for us is phosphor bronze. Then the structure oxoacids of a phosphorus. Oxoacids of a phosphorus structure is quite easy, very easy. See, the very first phosphorus is hypophosphorus acid. It is a monobasic acid. The term monobasic clearly states that even though that phosphorus acid, hypophosphorus acid has 3 hydrogen, only 1 hydrogen is replaceable or only 1 hydrogen is ionizable. Let us see the structure. See, H3PO2. So this is the whole formula, and if you write it, it is P double bond O, around which you will be able to find OH, H and H. So H3PO2, out of which only 1 hydrogen is ionizable actually. So that's why it is a monobasic acid. And if you look at the oxidation state of the phosphorus, here the oxidation state is +2. Right. See, it is quite easy to calculate the oxidation state over here. H3PO2, here this is the thing that you need to find. So 3 plus X minus 4 equal to 0. So here, here it becomes so it becomes 3 plus X minus 4 equal to 0. So X equal to X minus 1 equal to 0, X equal to 1. So that's it with this. Then the next one is orthophosphorus acid. Orthophosphorus acid is H3PO3. Structurally it can be written as P double bond O. In all the cases you are replacing an hydrogen with OH, that is it. So, this is H3PO3. So, it is a dibasic acid, 2 hydrogen is capable of replacing and the oxidation state over here is +3. The next one over here is right H3PO4, which is P double bond O, OH, OH and OH. So, H3PO4 and it is a tribasic acid, 3 hydrogen is capable of replacing and the oxidation state over here is +5, right. Then the next one is hypophosphoric acid. See, when I say hypophosphoric acid, when 2 hydrogen comes, 2 phosphorus comes, it is the bond happens in this way. So, here it is OH, 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 OH. So, this is the bond that happens over here. So, this is H4P2O6 hypophosphoric acid. It is a tetrabasic acid. All the 4 hydrogen which is present along with the oxygen are replaceable or ionizable. That is why it is tetrabasic acid. And pyrophosphoric acid. Pyrophosphoric acid here H4P2O7 along with this P double bond O, an oxide linkage is present between themselves, among themselves itself. Here it is OH, OH and OH, here it is OH. So, here also it is a tetrabasic acid because all the 4 hydrogens are replaceable. Now, let us go with the oxidation states here. Let us go from the last. See, phosphorus over here. So, 4 plus 2x plus 7 into minus 2 equals to 0. X phosphorus is the one that we need to find over here. So, 4 plus 2x minus 14 equal to 0, 2x minus 10 equal to 0, 2x equals to 10, x equals to 10 by 2 which is equals to 5. So, the oxidation state over here is 5. Then next one is here this hypophosphoric acid 4 plus 2x minus 12 equal to 0, 2x minus 8 equal to 0, 2x equals to 8. So, x will be equals to 4. So, the oxidation state is +4. Then next one is here tribasic acid which is orthophosphoric acid 3 plus x plus 4 into minus 2 equal to 0, 3 plus x minus 8 equal to 0, x equal to 5. So, the oxidation state is +5. So, this is how we need to calculate the oxidation state of these oxoacids of a phosphorus. Preparation of this oxoacids of a phosphorus is not in our portion. So, we are restricting with this, and here comes the end of the part 3. So, from now we will be having a short video so that you can just take a look at it, just going a drive along with your parents, or when you just sit at your home, when you are surfing with your mobile, you can just go through. So, in order to make it very comfortable for you, we are doing this short video, and hope you all will be able to manage with this and get utilized so that your knowledge can be enriched. So, I will meet you in the next part with the group 16, the oxygen family. See you all in the next class. Thank you.